Hello and welcome to the channel. This is effectively the problem from AMC 12A, year 2011. I only replaced equality sign by less or equal, since this way it looks more logical to me. In fact, this modification doesn't make a difference at all. Also, the conditions do not tell explicitly that x and y are real numbers. However, since maximum value is inapplicable to imaginary numbers, x and y must be real. So let me point that out to avoid confusion. It can be also noticed that all the answers are positive integers, which you may find useful. However, I'm not going to use that. Now it's a good time to pause the video and try solving on your own. For the solution, I used the following well-known inequalities, applying to any real a and b. The proof you can find in particular in one of my previous videos. What is really useful for the solution? When the product AB is non-negative, both inequalities turn into equalities. Therefore, if xy is non-negative, we can just replace the absolute value of x plus y with the sum of absolute values, and the absolute value of x minus 1 with a non-negative difference of absolute values. By adding up these inequalities, we get another expression for the left-hand side of the given inequality. Let's see what we get when xy is negative. In this case, x times negative y is positive. So we write that the absolute value of x plus y equals the absolute value of x minus negative y, and apply the equality to x and negative y. Now, since absolute value is an even function, we can drop minus before y. In the similar way, we can get the expression for the absolute value of x minus y. Again, we add up the equalities, and surprise! We get exactly the same expression as for case 1. So we can write one equality to suit both cases. However, does it really help solving the problem, given that the right-hand side looks even more complex than the left-hand side? What do you think about that? In fact, the right-hand side can be simplified, based on the fact that the absolute value of any real a is the maximum of a and negative a. Let's apply that to the absolute value of the difference. Now we can move the leading terms inside the maximum. This is our golden moment. Some terms are cancelled out, the remaining terms are merged. So we end up with a really compact expression, which can be made even smaller by placing common factor 2 outside maximum. So this is what is hidden behind the given inequality. And of course we can simplify it by dividing both sides by 2. Now we can forget about the original inequality, as we found a more convenient replacement for it, which can be represented as the system of simultaneous inequalities or the system of simultaneous double inequalities. The remaining part looks much easier to me. Try to complete on your own. So we have target function f of xy, which has to be maximized. Function f of xy can be represented as the sum of two functions, g of x depending only on x and h of y depending only on y. Therefore, the maximum value of f is the sum of maximum values of g and h. With function h it is really easy. Since absolute value of y does not exceed 1, y squared, which is the same as absolute value of y squared, cannot be greater than 1. Therefore, the maximum value of h is reached when y equals plus minus 1 and is equal to 1. For function g, we can either get a derivative or just complete it to full square. We see that the graph of g of x is a parabola with vertex coordinates 3 and negative 9, and since x squared appears with positive factor, The parabola points upward. In our case, the value of x are located between -1 and +1. All these values are less than 3, therefore located to the left of the vertex. This means that function g of x is monotonically decreasing for x in the interval from -1 to +1. So the maximum value of g of x corresponds to x equals -1, and that value equals 7. Now we have maximum values for both g and h and can find the maximum of f. The answer is 8, corresponding to point D. Let's highlight the answer for not forgetting it and consider a purely graphical approach suggested by our problem solving side. So we are looking for the values of x between -1 and 1 and the values of y in the same range. The intersection is a square. This time we don't split function f, but still complete the first two terms to full square. The result can be represented as d squared minus 9, where d is the distance between point P with coordinates 3, 0, and a point with coordinates x and y located inside the square or on its boundary. We are looking for the maximum value of f corresponding to the maximum value of d. And quite obviously, the longest distance to point P is reached at left corners of the square, points A and B, where x equals -1 and y equals ±1. For these values of x and y, d squared equals 17 and f equals 8, the expected answer. I would certainly place 17 among the answers, expecting that someone may forget subtracting 9. A great problem and good solution, but as everything, it has the end.